Okay, so welcome to the second talk of today. It is my pleasure to introduce Ivan Smith, who will speak about plumpings and flops. So please, Ivan.
Okay, thank you for the invitation to speak. So I don't really have a good sense of how to pitch this talk and what kind of level people are at, but I'm going to start in geometry and eventually I will reach some things that are closer to representation theory. But since I'm a geometer, I'll sort of tell the story from my point of view. So everything I'm talking about is joint work with Michael Weems at Glasgow. So Michael is a birational algebraic geometer. So he provides the flops half of the story and everything technical in the representation theory. Well, let me just start with one of the most classical questions that arises in symplectic topology. So I take a symplectic manifold. So you could think about, for instance, a smooth algebraic or quasi-projective variety. And I'm interested in the Lagrangian submanifolds of X. So I hope everybody will have seen, since you have a mini course on Fugaya categories, that Lagrangian submanifolds are things we care about. So you could think, for instance, of the real points of an algebraic variety defined over R. That's one of our sort of favorite sources of Lagrangians. And a very basic question we could ask is, what are the homology classes realized by Lagrangian submanifolds with certain geometric properties? So, for instance, we might ask about, exact Lagrangians or simply connected Lagrangians or Lagrangian spheres, some class of interest. So let's look at the simplest possible example. So the simplest symplectic manifold that's not zero-dimensional and has interesting Lagrangian submanifolds is just the cylinder, the cotangent bundle of the circle, which of course is a trivial bundle, so that's just S1 times R. Okay, and there's an interesting Lagrangian submanifold, which is the zero section. So in T star S1, I just look at the zero section of the cotangent bundle. And it's an easy topological kind of exercise that, this generates, the first homology Z of the cylinder. But if I take, for instance, twice the generator of the first homology, then I can only represent that by an immersed curve. Okay, so I can draw a kind of figure 8, and similarly, I could draw curves that wind some number of times around the cylinder. I could draw an embedded curve representing the zero homology class in the cylinder, just a little curve bounding a disk. Those tend to be less good curves from the point of view of symplectic topology and Floer theory, as you'll probably have sort of absorbed from James's talks. But, this is somehow a nice immersed curve, but it's still a perfectly natural question as a geometer to wonder about which homology classes are represented by embedded Lagrangians. Okay, so if I replace T star S1, where we have this easy topological argument, by almost anything, so for instance, I could look at T star S1 times T star S1. Okay, so you could just look at the product of the two pictures I've drawn with an embedded circle and an immersed circle. Okay, and inside the product, which is the cotangent bundle of the torus, the two torus, as I move around this loop, I could sort of slide this circle up and down a bit to completely avoid this self-intersection. So this class, which is twice the zero section in T star T2, is represented by a smoothly embedded torus. And there's no easy proof, but it's a fact that it's not represented by a Lagrangian torus. Okay, and so a general theorem in this vein, this is not the strongest thing we know, but is kind of emblematic of what we'd like to know, is that if I give you two simply connected manifolds, L and Q, and I tell you that L embeds as a Lagrangian in the cotangent bundle of Q with its canonical symplectic structure, then up to sign, L is homologous to the zero section. Okay, so this is a sort of, I think, strong and non-obvious constraint about Lagrangians in cotangent bundles. One source of more interesting symplectic manifolds than cotangent bundles is plumbings of cotangent bundles. So the plumbing operation involves taking two cotangent bundles, here the cotangent bundles of M and N, and I fix points in each of M and N and the corresponding cotangent fibers through those points. And now I'll glue those two cotangent bundles together, but in a way that sort of glues together base directions with fiber directions in the respective copies. So the sort of schematic sketch is that I have a manifold which contains the one-point union of M and N, and it's some kind of disk bundle over that, but obviously something more complicated happens near the intersection point. Okay, and this is familiar in lots of, simple examples. So punctured surfaces arise by plumbing together copies of the cotangent bundle of the circle. So if I just plumb together two copies of T star S1, so that's drawn here, you see one circle here and the other one running through this loop, okay, and they're meeting at exactly one point. And up to isotopy, the plumbing is just a once punctured torus. Okay, so now the first homology of our once punctured torus has rank 2. We see some obvious Lagrangian circles coming from the curves that we started with. Okay. And it's a well-known, again, easy exercise in surface topology that the classes in this lattice that are represented by embedded circles are exactly the classes with coordinates P and Q, where P and Q are coprime. Okay, and in this case, we can actually obtain all of these interesting embedded Lagrange circles from a group action. So if I give you a circle in a two-dimensional surface, there's an associated Dane twist, which takes a sort of small cylinder around this circle and cuts it open by twists by 2 pi and re-glues. So a curve that used to go like this will afterwards go sort of twisted around the cylinder. And by twisting along these A and B curves, I can realize all of the things that are realized, all of the homology classes represented by simple closed curves in the punctured torus as sort of built out of an action, in fact, of the braid group on 3 strings, which reflects this relation in Dane twists. Sort of all of the interesting circles are braid group images of my favorite one, for instance, this circle A. Okay, so this is, again, a low-dimensional example. If in higher dimensions we look at the analogous spaces, we also know a great deal. Okay, so now the higher dimensional cousin of this once punctured torus is that I take 2 copies of the cotangent bundle of Sn, and I again plumb them together at a point. So I build a symplectic manifold which retracts to a union Sn wedge Sn. In fact, it's known that this space, which is usually called the A2 Milnor fiber, is actually just an affine variety. It's given by this equation, sum of variables squared plus z cubed is 1. So it's a hypersurface in Cn plus 1 with just the standard symplectic structure of Cn plus 1 restricted to the hypersurface. What's maybe not so obvious is that whenever I have a Lagrangian sphere in a symplectic manifold, there's an analog of this Dane twist in an annular neighborhood of a circle. So this is a symplectomorphism, which I'll call tau sub L. It's actually compactly supported near this sphere. So globally, it looks like a compactly supported symplectomorphism of the cotangent bundle of Sn. And it's also known for this high dimensional cousin of the punctured torus, this A2 space, that the 2 Dane twists, one in this sphere and one in this sphere, braid. So the two twists generate an action of the braid group of three strings by symplectomorphisms. I can then move a Lagrangian submanifold I understand by an element of this symmetry group, and I'll get a new symplectomorphism. And actually, the braid group is acting transitively on the homology classes of Lagrangian spheres. Again, up to some question of sign, because Lagrangian submanifolds are not canonically oriented. Okay, so now in this case, this is not an easy theorem to prove, but it's a theorem that we know. It has a sort of reasonably constructive proof. So the story I want to talk about today, which connects to a couple of different things, is a minor variation where I take n equals 3, but instead of gluing two copies of the cotangent bundle of S3 together at a point, I want to glue them together at a circle. So I'll have sort of, it's slightly hard to draw this, but sort of two S3s, and they'll come together and cleanly meet along a circle. Okay? And what you could think of is that as I walk along this circle in the normal bundle, sort of in transverse directions, I see the two-dimensional version of this story. But so I can form this plumbing that I call a double bubble plumbing, because it looks like two bubbles glued together. And I'll take a simple situation in which the circle in S3 is just an unknot, it's a linear circle. But to build this manifold, this plumbing of two cotangent bundles along something that's more interesting than a point, so what I'm doing is some two-dimensional story in each fiber of the normal bundle to this circle. And there's a possibility to twist the story somehow as I walk around the circle. So it turns out that the construction of this manifold relies on choosing a trivialization of the normal bundle to S1 in S3. Okay, so that's a trivial bundle. So different trivializations of this bundle just correspond to maps from S1 to GL2, the symmetry group of the disk, and that has fundamental group Z. So there's an integer family of these plumbings I can build. And there's actually some sort of redundancy because there's some symplectomorphism that lets me change a sign. So it turns out that there's a sequence of plumbings indexed by the natural numbers that I'll call Wn, W0, W1, W2, etc. And geometrically, we'll come back to this in a few slides' time. One way of understanding the difference between the Wi's is that inside the total space of this symplectic six manifold, I can smooth out these two three spheres which happen to meet in the same way that if I took two circles or two arcs in the plane, I could smooth out their intersection and replace this by this. Well, I can just do this at every point along this circle and obtain from my core three spheres Q1 and Q2 a more interesting three manifold that I get by sort of doing a surgery of them. And what that three manifold is depends on this normal bundle data. So when n is 0, I get S1 times S2. When n is 1, in my convention, I get the three sphere. And for larger n, I get a quotient of the three sphere, so the lens space, Ln1. Okay, so this is already slightly more interesting than the geometry I could see in these A2 spaces, where when I smooth out this intersection, I just get another sphere. Okay, but now it might be that the new thing I get by doing some surgery is not a sphere. So I'd like to ask this question: what can I understand about Lagrangian submanifolds of these double bubble plumbings? Okay. And so the theorem, we prove maybe a bit more than this, but one theorem, which is joint work with Michael Weems in progress, says that if I take a Lagrangian three sphere in one of these plumbings, well, if I'm in this case where the surgery of these two core three spheres was itself a three sphere, I certainly know that I can realize the homology classes of either Q1, Q2, or their sum by 3 spheres. Those are the things I visibly see. And the theorem says that up to some sign issues, that's everything. On the other hand, if I is bigger than 1, we expect that, so that's a situation where this kind of surgery type Lagrangian is now a lens space, so it's not a 3 sphere. So we would guess that the only Lagrangian spheres that you can find live in the homology classes of these sort of input spheres Q1 and Q2. And what we can prove is that that's true if I is bigger than 2 and prime. Okay, so before the situation was that all the Lagrangian spheres that we knew about came from some braid group action. So I still have Dane twists, Tor Q1 and Tor Q2 in these kind of given spheres. And it's actually a beautiful theorem of Elster-Keating that these generate a free group, this time not a braid group. But this is, first of all, not the whole group of interest that's acting. I mean, in the case of W1, I've said that there's the third 3 sphere that lies in the class Q1 plus Q2, and the Dane twist on that will be another interesting symplectomorphism of this space, and it's not part of this free group. So we shouldn't really expect this free group to let us simplify everything. On the other hand, what one can check fairly easily is that this group acts trivially on the homology. So finding no interesting new homology classes is compatible, and this is somehow essentially what we'll show, with all Lagrangian spheres behaving like they come, well, not quite from this group, but from a slightly larger group that acts. Okay, so this is a theorem I want to talk about. But now we're going to take a kind of longish digression and talk about quivers and potentials on quivers, which is probably a story that's more familiar to many of you than to me. So a quiver is a directed graph, okay? And a potential on a quiver is a formal linear combination of oriented cycles. Okay? So in, for instance, this very simple graph, which is just an oriented 3 cycle, you know, the different cycles I have are the basic EFG or powers of this, and of course their cyclic permutations. And a potential is some linear combination of these. Okay, and in this slightly more interesting graph, I have slightly more interesting possible cycles, not just multiples one of another. So this is a elementary kind of thing. So there's an operation, I think, introduced by Kontsevich, at least Ginsberg, I think, attributes it to him, called the cyclic derivative, which lets you differentiate a cyclic word in the arrows, like one of the monomial terms in this potential, in the direction of some particular arrow A. Okay? And the formula for the cyclic derivative is this. So it says, you take your word W, okay, so this is some cycle of arrows, and you've got some fixed arrow A in mind, and you think about the ways that A shows up somewhere along W, and then you think about breaking W at A and just taking the sort of the rest of the word. Okay, so that's expressed in this. So if, for instance, I had one of these iterated cycles that wraps around this triangle twice, EFG, EFG, and I took its cyclic derivative with respect to F, well, I would cycle around to put an F at the beginning by moving this E to the back, and then I differentiate with respect to F, which would knock the F off, and I'd get this term. But I could also cycle around all of these terms to the other side to get an F at the beginning, and then I get another term which happens to have the same format. That's sort of not so surprising because this itself was, you know, the square of some cycle, so its derivative should be twice something. Okay, and the Jacobi algebra of the quiver with potential is the path algebra of the quiver modulo the ideal generated by the cyclic derivatives of the potential. And it's a kind of empirical fact that these are often CY3 algebras. That's to say that their derived categories of modules have a kind of Serre duality property in dimension 3. And more generally, Ginzburg showed that this Jacobi algebra is always the sort of zeroth cohomology of some correction to the Jacobi algebra, which is now a DG algebra. So this is graded in non-positive degree, and so its top cohomology is a Jacobi algebra, and this thing is always CY3. So one should sort of think of the Jacobi algebra as the thing it's reasonable to define quickly, but not quite the right object. The right object is this sort of CY3 gadget. And it's a general problem in, some part of algebra to find geometric models for these particular DG algebras, or the CY3 categories that arise as their categories of modules. And so by geometric models, well, I'm sort of naturally symplectically inclined, so I think about a geometric model being a Fukaya category, but you could also think about looking for a realization as the derived category of sheaves on some Calabi-Yau threefold. So there's some hope that if you meet a Calabi-Yau category, there might be an actual Calabi-Yau in the background. So one source of quivers with potential that, of course, was enormously elucidated by vast amounts of difficult algebraic work of Daniel and others, is the quivers with potential associated to triangulated surfaces. And in that case, there's a reasonable answer to this. So these CY3 categories can be understood in terms of Fukaya categories of certain symplectic 6 manifolds that you can associate to a 2-dimensional surface. But quivers with potential associated to triangulated surfaces are only a kind of, one source of these algebras, and hence these categories. Okay, so for a symplectic person, it's actually easier to start with a causal dual viewpoint on the Ginzburg algebra. So we still have a quiver with potential, but we're going to do something different, and I'm going to describe this in a bit more detail. So for each vertex V in the quiver, we're going to start with a spherical object. So remember, I'm interested in the sort of CY3 properties of this category. I'm looking for something that looks like the derived category of sheaves on a 3-dimensional Calabi-Yau. So by a spherical object, I mean I'm going to try and build a category C, and this object should have endomorphisms, the cohomology of a 3-sphere. And then the algebra I consider will have underlying graded vector space, the direct sum of the morphisms, the graded morphism groups between these spherical objects. Okay, so the morphisms from one of these LVs to itself live in degrees 0 and 3. It's given by the cohomology of S3. If I take 2 different vertices V and W in my quiver, then the arrows from V to W give me a basis for the degree 1 homomorphisms from LV to LW. But if this is going to have a CY3 property, then the degree 2 morphisms from LV to LW should just be the degree 1 morphisms from LW to LV dual. Okay, and I know how many of these there are. It's based by the arrows from W to V. So at least if my quiver has no loops, so it's really true that the degree 1 things always relate a pair of different vertices, so that's needed for this condition to hold. So if I have a loopless quiver, then I get, a graded vector space from this, and I would like to define not quite an algebra structure, but an A-infinity algebra structure on it. And the terms in the A-infinity structure are dictated by the terms in this potential. So the cubic terms in the potential actually tell me the product in my algebra. Okay, so how does the general story go? So an A-infinity, the mu2, the product part of the A-infinity structure, should give me, maps from Homs from V0 to V1 tensor Homs from V1 to V2 to Homs from V0 to V2. And mu2, of course, is a degree 0 operation, it just adds degree. But we've just said that the degree 2 morphisms from V0 to V2 are dual to the degree 1 morphisms from V2 to V0. So if I take that sort of dual over to the other side, specifying this mu2 operation is exactly the same as specifying a sort of operation on this tensor product cyclically ordered of degree 1 morphism spaces from V0 to V1, V1 to V2, and then V2 to V0. So what I want is an operation involving 3 inputs and giving me an element of the ground field. Okay. Well, the cubic terms in the potential I can exactly think of as giving me a non-trivial coefficient to this triple of arrows, which are 3 different degree 1 morphisms. And if there was a coefficient here in the potential, that would be the value of my mu2. Okay, and then exactly analogously, if I have a higher order monomial in W, well, that's giving me, if it's a 5-gon or more generally an n-gon, it's giving me a mu4 or more generally a mu n-1, but understood from this cyclically symmetrized perspective. And it's a sort of easy argument basically just to do with degrees, that whatever potential formal word in cycles you take, the resulting algebra you write down, the A infinity structure really is one. That's to say the A infinity relations hold. Okay, so from this point of view, the simplest quiver, which admits an interesting potential, is the oriented 2-cycle. Okay, this is the simplest loopless quiver in which you can actually form a cycle of arrows. So if you were looking for a kind of geometric picture for this, what should you do? Well, you should have 2 vertices, which means you should have 2 3-spherical objects, okay? And that sort of should remind you of these symplectic manifolds that we were talking about a little while ago. And just to comment, I said that the algebra structure is determined by the cubic terms in the potential, and the higher terms record higher A infinity products. So it's a sort of standard fact that you don't really want quadratic terms in your potential. So we're really interested in potentials that are only cubic or higher. And then it's an easy check that up to formal change of variables, the potentials you can have are just the monomials EF to the n for some power n. Okay, so we would like to find geometric models for the 2-cycle quiver equipped with the potential EF to the n for some n at least 2. So let's go back to my double bubble plumbings. Okay. How should one think about these spaces Wi that I introduced before? So one nice way to try and think about symplectic manifolds, which is often useful from a Floer theory point of view, is as Lefschetz vibrations or cousins of Lefschetz vibrations, but in any rate as the total space of some kind of singular vibration over the complex plane. That's useful because then you can project holomorphic disks to see where you understand them pretty easily. Okay, so these spaces Wi admit vibrations over C whose general fiber is C star times C star, the cotangent bundle of a torus. And there are 3 singular fibers, each of which abstractly looks like C star times C union C. Okay, so there's a standard kind of picture that you might easily visualize in which C star degenerates to a singular cone. And of course, a singular cone is just the union C. So what we're seeing is a sort of higher dimensional cousin of that, in which this degeneration happens in a whole family parameterized by another copy of C star. So this is what's called a Morse-spot Lefschetz vibration. The singularities are kind of transverse in normal direction. But from this viewpoint, it's easy to see these kind of core three spheres that we put into the construction. Okay, so I have a fibration whose general fiber is a torus, okay, and I've marked the A and B circles on the torus. And imagine what happens if, as I go into one singular point, I parallel transport that torus, but the A cycle collapses. So at the end, this torus, the sort of real part of T star T2, just ends up, if the A cycle collapses, being a circle in the class B. But if at the other end of this path, the other circle collapses, then over here I see a circle in the class A. But what I've described is exactly the genus 1 Heegard splitting of a torus. I've described two solid tori glued together in such a way that I get S3. So there's a picture of WI in which, here's a little schematic for my torus as an identification space. One of the three spheres exactly arises this way. The circles that collapse in the torus at the ends are the A and B circles. Okay. But for the other torus, for the other three spheres, sorry, the circles that collapse are not B and A, but B and some other circle in the torus, say A plus IB. Okay. So these two still span the integral homology of T2. So this object is still a three sphere. But if I now imagine trying to build a Lagrangian that fibered over a path between these outer two critical points, the circles that collapse at the ends would be A and A plus IB. So those don't span the homology of the torus. They only span a sort of finite index subgroup. And what I get over such an arc is a Lagrangian lens space, which I'll call K. Okay, so this is a sort of geometric picture of these spaces. And if we want to see, how and if they relate to quivers with potential, then what we should do is compute the A infinity structure, the endomorphisms in the Fukaya category of the object given by the sum of these two three spherical objects, these two Lagrangian three spheres. Okay, so Floer cohomology in general is sort of not so easy to compute, but the Floer cohomology of a Lagrangian with itself is some kind of approximation to the cohomology of the Lagrangian. And if the Lagrangian bounds no holomorphic disks, it is the cohomology. And it's not hard to see from this picture that these Lagrangians can't possibly bound any holomorphic disks, right? If I had a holomorphic disk with boundary on this Lagrangian and I project to C, well, I get a holomorphic disk whose boundary lies in an arc, so it must lie in a fiber by the maximum principle. But in the fiber, my Lagrangian is a torus inside T star T2. But that sits there pi1 injectively, so it can't bound any interesting disk. Okay, so it's easy to see that the Floer homology of Qy with itself is the cohomology of S3. And a cousin of that argument says that the fact that these two three spheres meet in a circle, which is the circle that survives in this singular fiber here, says that the cohomology between them graded looks like the cohomology of a circle. So in fact, it's degree 1, rank 1 in degree 1, and also rank 1 in degree 2. So that sort of immediately tells you that the graded vector space we're seeing is the vector space that underlies this two-cycle quiver. Okay, so I will come back to quivers with potential and the first step in this argument at some more length in a little bit, but I'd just like to give a kind of four-step overview of the proof of this theorem about homology classes of Lagrangians, so that those people who come from algebra and are feeling bereft and tired of all of these Lagrangian submanifolds have something to kind of hang on to. Okay, so our goal is to understand this 8-dimensional A infinity algebra and then use it for something. I mean, find some use in the answer. Okay, and as I've hinted, the first step is to show that this A infinity algebra is basically the same one that comes out of the Ginzburg construction applied to the two-cycle quiver, equipped with the potential EF to the I to some power, but that relies on working in a particular characteristic, okay? And I think that I've got a slight typo. This should be EF to the I plus 1. Don't quote my indices. But in any case, it should be EF squared should correspond. So EF squared corresponds to the space that I was calling W1, and here you should work in characteristic 0. Whereas EF cubed would correspond to the space I call W2, and EF, to the 4 corresponds to the space that I call W3, and we get these equivalences only in a characteristic that depends on the geometry. So there's a sort of major kind of technical headache here that one has to carry all through the work, which is that this cyclic derivation property, the idea of cyclic derivative, is not very well behaved in finite characteristic. One doesn't usually talk about quivers with potential in finite characteristic, but somehow, the underlying A infinity algebras, the idea that the possible monomial terms that you see in an expression like this tell you all the non-trivial A infinity products, that's a reasonable idea over any field. So sometimes I'll use the language of quivers with potential, but it's being used slightly abusively. Okay, so one of the key places following work of Vandenberg, Donovan, Weems, and others that quivers with potential do arise is in birational geometry of threefolds. And in particular, when you study rational curves in a threefold that can be flopped. Okay? So you can write down the following very explicit threefold. It's defined over Z and hence over any field. Okay? It depends on some parameter I, and it has an isolated singularity at the origin, and this singularity has the special feature that it admits a so-called Crepent resolution. That's to say you can resolve it only gluing in curves rather than divisors, so not changing the canonical bundle. And what you actually glue in is 2 rational curves which meet at a point. Okay? And then you get a smooth threefold xi. Each of these curves has normal bundle O minus 1 minus 1, and you can study inside the derived category of sheaves of xi, the part of the derived category just involving sort of the simple line bundle O minus 1 supported on either this curve or this curve. And that gives you 2 objects which by sort of standard theory of threefolds turn out to be spherical. And you can do some work and understand that piece of the derived category and find that the same quiver with potential shows up. Okay, so we have sort of 2 little categories. There's a category I'm calling Qi. It's the part of the Fukaya category of my threefold Wi, which is generated by these 2 3 spheres I started with. I also have a category Ci, which is part of the derived category of this threefold resolution. Okay? It's characterized as those sheaves supported on the exceptional locus, which push forward to 0, but you should just think of it as generated by the O minus 1s on these 2 exceptional P1s. Sorry, this was an OP1 minus 1, but there are 2 P1s in play. And direct computation basically says that these 2 categories are equivalent, provided I work in the right characteristic. So it's also true that there are braid group actions extending the free group I mentioned earlier, generated by the 2 obvious spherical twists. They're actually now pure braid group actions on both sides here. On the symplectic side, they're generated by the 2 Dane twists in the Lagrangian 3 spheres I fed in. And I told you that the surgery of these 3 spheres was a lens space. And it turns out that, the Dane twist, which is a certain symplectomorphism of T star S3, commutes with the finite group action on S3 that defines a lens space. So there's also something called a lens space Dane twist. And these three maps together generate an action of the pure break group. And in case it seems mysterious that the pure break group should arise, let me just remember that we've seen a picture of this threefold in which 3 points in a plane, the critical points of our Morse-Bott-Lefschetz vibration, played a geometric role. So this pure braid group arises by allowing these 3 points in the plane to move in the plane. Okay, so it has a very geometric origin here on the symplectic side. As is often the case in sort of mirror symmetry type scenarios, the sort of braid group action on the B side is more involved, and it's built out of sort of chasing mutation functors around some complicated groupoid, to my mind. Okay, so this equivalence of categories entwines certain group actions. So why is that a good thing to know? So we're trying to understand Lagrangians in this manifold. So we're trying to understand Lagrangian objects, maybe spherical objects in this category. And a good way to understand them, following what worked for our simple example of a punctured torus or its higher dimensional cousins, is to show all such Lagrangians come from one or at least finitely many orbits under an action of a symmetry group. Okay, but one still needs to carry out that kind of inductive analysis or simplification, and that's really where the representation theory arises. So on the B side, this category of sheaves has somehow shown up naturally inside the derived category of my threefold X. But there's a different model for this. This category also sits in the derived category of modules over a certain algebra, lambda. And lambda has the property, I mean, I'll say something about a certain quotient of it later, which is called the contraction algebra. And this derived category, or maybe I should say, you know, this T structure on this derived category turns out to be a simpler place to do homological computations. Okay, so concretely, you know, the real work comes down to thinking about a spectral sequence of the following shape. We have some module or some element of the derived category of modules P, and we would like to understand consequences of P being spherical. And we'll use a local to global type spectral sequence of this shape. So immediately, symplectic topologists are kind of, you know, forced out of their comfort zone, because any spectral sequence of this shape is using the internal cohomology sheaves of P. It's using the fact that we're working in the derived category of an abelian category, and the Fukaya category isn't that. Okay, so the left-hand side of this spectral sequence, I mean, mirror symmetry says this right-hand side is some kind of Floer cohomology of the Lagrangian corresponding to P that I care about. But this left-hand side has no symplectic interpretation in general. And it's the ability to access this that makes going through an equivalence like this worthwhile. Okay, so let me spell out a little bit more about some of these steps. So where does this first key step one, the fact that we can relate this symplectic manifold to the quiver, come from? Okay. So I said that we'll be interested in this Lagrangian K, the surgery of the two cores, okay, and a general fact in symplectic topology is that this geometric surgery is represented by a mapping cone in the Fukaya category. Okay, so Q1 and Q2 were the vertices of my quiver, and there was some degree 1 morphism between them, and I can take the mapping cone of that morphism. It corresponds to the fundamental class of the S1 intersection locus between Q1 and Q2. But that tells me something kind of fantastic. This thing is an exact Lagrangian submanifold. So that means that we know everything about its Floer cohomology. It's the same as its ordinary cohomology, but not just as an algebra, as an A infinity algebra. So the endomorphisms in the Fukaya category of this mapping cone should reproduce for me the cohomology of this lens space. And of course, the cohomology of a lens space differs very much whether you work in characteristic 0, where it looks just the same as the cohomology of the 3-sphere, or characteristic determined by its fundamental group, in which case it behaves more like a real projective space. Okay, so the fact that H2 of the lens space integrally is Z mod I exactly turns out to mean that, you know, in twisted complexes over the Fukaya category, some particular differential is non-zero. And if you unwind that, it's exactly saying that there's necessarily a quartic term in the potential. So in characteristic 0, you know, this coefficient is not interesting. Up to some formal change of variables, my potential is EF squared. Okay, so all of the categories Qi associated to my different spaces Wi, if I work over C, are quasi-isomorphic. They're all given by the two-cycle quiver with the quartic potential. At least if I is not 0. If I is 0, I actually get the formal category. But clearly, if I is some prime P and I work in characteristic P, then this PEF squared term, whose existence I just argued for, disappears. Okay, but that was sort of coming from knowing the cohomology groups of the lens space. I actually know more about the cohomology of a lens space. It's a classical fact that with Z mod P coefficients, the lens space LP1 has a non-trivial higher A infinity product. If I took not the finite dimensional lens space, but the infinite dimensional lens space, okay, so this of course is an Eilenberg-MacLane space, KZ mod P1, right? Then its classical cohomology is just the Ext algebra over the group ring of Z mod P of the simple module, and the existence of this higher product is a very classical thing. Okay. So starting from that, somehow direct computation lets you show that in characteristic P, this piece of the Fukaya category of my symplectic manifold is governed by this potential. So on the B side, one has to carry out some similar direct analysis. There, the sort of strategy is a bit different. You no longer have a geometric interpretation for this mapping cone. So, you know, we can still form the analog of the right-hand side of this, a mapping cone on the two sort of O-1s over the basic curves of the resolution. But, you know, there's nothing geometric that gives us a shortcut to understanding it. So the arguments go via introducing what's called an Adams grading and pinning down A infinity structures that way. Once one has this equivalence, it's more or less immediate that it relates the basic objects Qi to these basic sheaves. And since the twist functor in a spherical object is determined almost by the object and a little bit of extra data, it's then not so far to see that this equivalence is actually sort of braid group equivariant. Okay, so there's kind of an addendum to this. So we have these categories Qi and Ci. Really what I'm interested in for symplectic applications is the Fukaya category of Wi, and this is a priori just a small piece of it. So one has to check that over the appropriate coefficient field, this actually generates the Fukaya category, so it contains all the objects you care about. We also started by introducing quivers with potential from the viewpoint of causal duality. And causal duality has played kind of an interesting role in symplectic topology in recent years, following work of sort of Ekholm and Likili and Yin Li and Sheel Ganatra and others. And in many cases, it's understood that there are two flavors of the Fukaya category, one that includes compact Lagrangians, like these spheres and lens spaces, but one that includes non-compact Lagrangians. So in the simplest case of T star Q, I have both the zero section Q, but also the non-compact cotangent fiber. Okay? And I can introduce a form of the Fukaya category which allows the cotangent fiber, that's the wrapped category, which in this case is just the Ginzburg algebra of my quiver with potential. So this is A infinity causal dual to the Fukaya category. And it's not quite the derived category of my threefold, but it's very closely related. It's the quotient of that by the structure sheaf. So why is this useful? Well, for sort of, arguments that go back quite a long time, if a symplectic topologist came, just one fine day across a manifold like WI, a plumbing of cotangent bundles, they would understand that to analyze exact Lagrangian submanifolds, what you should do is think about this and try and understand the wrapped Floer cohomology of the cotangent fibers to these basic QIs. So the things that sort of sit here, the non-compact Lagrangians, and try and understand their representation theory. So there's a sort of quite general setup in which the modules, the A infinity modules associated to Lagrangians are filtered by modules over the A infinity algebra associated to these non-compact Lagrangians. But in general, we would have no way of computing these wrapped Floer cohomologies. Okay? But here we certainly know what the Ginzburg algebra of this simple quiver with potential is. And in particular, in degree 0, you just get the path algebra of this quiver modulo the ideal, that relation of relations that paths of a certain length vanish. So for I equals 1, this corresponds to the potential EF squared. It's the relation that paths of length 3 vanish. And so this algebra is a fairly simple concrete algebra, and you can now go and study it. So it turns out to have 6 indecomposable modules. Okay, so when you come to think about this spectral sequence I mentioned before, you want to think about the cohomology sheaves of some complex P. So you're really interested in modules over this contraction algebra, and there are just not so many options. And in fact, this sort of final stage of the argument turns into an exercise in kind of tilting theory. So this is obviously not something that I could do. I've been kind of watching Michael Weems, my collaborator, manipulate tilting and knitting very fluently. So you construct the Auslander-Reiten quiver of this particular contraction algebra, okay? And we define for a module P a kind of complexity, a sort of length, which is a homological measure of complexity, which is the difference between the max and min degrees in which it has non-trivial cohomology. So we have this spectral sequence, and the very bottom left part of this spectral sequence is E2 0, minus L, where L is this complexity. And just for general reasons, this survives to E infinity. But if I start with a module that corresponds to a Lagrangian submanifold, a Lagrangian submanifold only has Floer cohomology in degrees greater than or equal to 0. So all the negative x of that module must be 0. Okay? But if this survives to infinity, that means that the 0 minus LP piece of this E2 page should be 0. So it tells me that certain cohomology modules of this complex are orthogonal. But there just aren't very many modules over this algebra that have the property that they're orthogonal. Okay, so the sort of technical lemma proved by knitting is that 2 indecomposable lambda con modules that are orthogonal have the, so if I give you 2 that are orthogonal, one of them is filtered by a unique simple module. So given this, it's then a sort of, bookworking exercise with spectral sequences to find that you can apply an element of the pure break group which decreases this complexity measure. But once you decrease this complexity measure all the way to 0, you find that actually up to the pure break group action, your unknown Lagrangian submanifold is just some indecomposable module. Okay? And well, a Lagrangian submanifold, if it's connected, doesn't just have no negative Floer cohomology, but HF naught is rank 1. And there are only 4 modules over this algebra that are simple, that are indecomposable and simple. And they exactly turn out to correspond geometrically to the two core spheres that I started with, and the two ways that I could have drawn this Morse spot surgery, either by a path that goes here above these, or by a path that goes along the bottom. So the geometric things that we see turn out to match up very beautifully with the output of the representation theory. Okay, I'll stop there. Thank you for your attention.
Thank you, Ivan. And there seems to be a question in the chat, and I think it's related to when you explained this degree 3 potential inducing a map.
Okay, how do I see the chat?
Yeah, so maybe let me read it. Is this map from the tensor product of 3 home spaces to the ground field some kind of trace?
I mean, you know, very loosely maybe. I mean, somehow the algebra structure in Floer cohomology, just the mu2, satisfies kind of, you know, it becomes the usual intersection product in, you know, ordinary cohomology, which satisfies Planck radiality and is non-degenerate. So you can interpret it in terms of a trace. But, you know, for me, I'm thinking about all of the mu i's as on the same footing. So this cubic sort of, this map from the tensor product of 3 home spaces to K is on the same footing as the maps from all the higher order cyclic products to K. So I don't know if that's, yeah, maybe that's a helpful way of thinking, but it's not how I usually think.
Are there any other questions? Yeah, so maybe like in the end you say use mutation, right, to decrease
Yes.
the p.
Yeah.
Yeah. So can you say something like so what mutation in which sense?
Right. So so it turned. I mean, so on the algebraic geometry side, the twist functor in a spherical object admits something that behaves a bit like a square root in this dimension, which is what's called the flop-flop functor. So there turn out to be 6 different Crepent resolutions of this singularity. And in this simplest case that's illustrated on this slide that I was thinking about, corresponding to my EF squared potential, there are canonical functors that move between these different sort of the derived categories of these different resolutions. And you know, those flop-flop functors, they correspond to mutating the quiver with potential. But if I mutate this quiver with potential, then up to sort of standard reduction, in the case with the quadratic potential, I just get back exactly the same thing. And in the case with the higher order potential, there are 2 sort of models. There's this model, the 2-cycle quiver, and there's actually another model that involves something that has a loop at one vertex. So there turn out to be 2 models, but I sort of shuffle back and forth between them. So the mutation is somehow really, it's not quite true to say that you can apply one of the spherical twists to decrease this. You actually apply these kind of flop-flop functors.
And now that you mentioned, I mean, this mutation of quiver with potential, I mean, somehow it's kind of a, like, let's say, more general version than that of Derksen, Neumann-Celebinsky, because it somehow can be done for 2 in the presence of 2 cycles, maybe loops.
Yeah, so I think 2 cycles are not somehow problematic, provided you can simplify the thing you get afterwards. I mean, yes. So I'm surely not the right person to answer this, because, you know, it's not that we're actually using mutation with quivers for potential. We're manipulating around this collection of, you know, derived categories of resolutions. But I think that at least in characteristic 0, where this language is at all appropriate, which is usually not where we're working, then it's okay to mutate a quiver with a 2-cycle in the potential if either you can simplify to get rid of the loops, or you're happy to move out of the realm in which you only have spherical objects.
Thanks. So Bernhard Keller says that it is Iyama-Yoshino mutation in the chat.
Okay, thanks.
Are there any other, thank you, Bernhard. Are there any other questions or comments? If not, let's thank Ivan again. And also, let me remind you that we are moving to gather.town for some virtual socialization. The passcode being Fukaya, all in lowercase. And then, well, see you there. Okay, thank you, Ivan.
No.
Bye.